Today we're going to review partial rates of change. More specifically, we'll take a look at finding partial derivatives as well as writing second partial derivatives and their matrices. This can all be found in section 7.3 of your lecture guide. So let's get started. We can begin by understanding the definition of what a partial derivative is. Derivatives of multivariable functions, meaning a function including both an x and y variable, for example, are called partial derivatives because they describe change in only one input direction. So they give only a partial picture of change. The function f of xy has two partial derivatives. The partial derivative of f with respect to x is found by treating x as the variable and all input variables other than x as constants. The partial derivative of f with respect to y is found by treating y as the variable and all input variables other than y as constants. In remembering our derivative rules, we should understand that by treating the input variables other than the primary variable as a constant, we apply the constant rule. This states that when you have a function equal to b or a number with no variable attached, your derivative is equal to 0. I've also included the notation for partial derivatives. On the left of the equal sign, you see the symbolic notation, and on the right, you see the notation read as f sub x or f sub y. Both forms mean the same thing, so it's really up to you which you'd rather write. To find partial derivatives, we'll resort back to our traditional derivative rules. The difference now is that based on the notation, you'll be taking a derivative specifically for one variable while treating the other as a constant. Looking at the example, we're given f of xy equals 3x plus x squared y plus 5y squared, and asked to take the partial derivative of x and the partial derivative of y. We'll start with x. It's important to interpret the function as its own separate expressions in order to apply the derivative rules. You can find a quick review of all the most important derivative rules in my first video about rates of change. So start with 3x. Because x is a variable we're acknowledging, we don't treat it like a constant. We use the power rule to find that the derivative of 3x is equal to 3. Next, we have x squared times y. Again, because x is included in the expression, we don't treat it like a constant. We apply the power rule again to get 2xy. Finally, we have 5 times y squared. Our primary variable of x is not included in the expression, therefore we act as though this is a constant. Remember that a constant is a fixed number. In this case, we understand 5 times y squared as being really no different than, say, a value of 50. The derivative of a constant is always equal to 0. A partial derivative of a partial derivative is called a second partial derivative. The simple multivariable function f of xy has 4 second partial derivatives. These are f sub xx, f sub xy, f sub yx, and f sub yy. Similar to the second derivatives of single variable functions, second partial derivatives measure how quickly rates of change are changing and indicate concavity. Recall the function f of xy equals 3x plus x squared y plus 5y squared from earlier slides. The first partial derivatives are shown at the top of this slide, these being f sub x equals 3x plus 2xy and f sub y equals x squared plus 10y. Finding the second partial derivative just means taking the derivative once again, but this time of your first partial. So looking at f sub x, to find the second partial with respect to x, we first see 3 and understand that because it's a constant, its derivative is equal to 0. We then take 2xy and again apply the power rule, but because the power on x is 1, it cancels out, leaving us with 2y. Next, we look at f sub xy, meaning the partial derivative of f sub x with respect to y. Again, the derivative of the constant 3 is 0, and apply the power rule, this time to the y variable, to leave us with 2x. The partial derivative of f sub y with respect to x is equal to 2x, because using the power rule, we bring the exponent 2 down in front of the x variable and subtract 1, while then treating 10y as a constant whose derivative is equal to 0. And finally, f sub y with respect to y gives us a value of 10, because x squared is treated as a constant whose derivative is also 0, and the power rule cancels out the y variable. The matrix of a second partial derivative will be used in later chapters to classify optimal points. Right now, you should just understand how to organize the matrix. As this slide shows, the values are organized in brackets with f sub xx in the upper left, f sub xy in the upper right, f sub yx in the lower left, and f sub yy in the lower right corners. Just a hint, the diagonal that's circled above should always have the same pair of values. This is a good way to check your work. As you can see in the completed matrix, the upper right and lower left values are both 2x. Today we discussed finding partial derivatives as well as second partial derivatives and their matrices. If you'd like some more individualized help, make an appointment with a tutor through the Academic Success Center and they can give you some more tailored support.